Twice a day, billions of people perform the same quiet ritual. We press a plastic tube to extrude a glossy, striped ribbon of gel that holds its shape against the pull of gravity. This paste exists as a chemically unstable suspension, holding dozens of incompatible ingredients in a delicate, temporary balance. The material switches its physical behavior based on the load applied to it. It remains a rigid solid while resting on the bristles, then transforms into a lubricating fluid the moment it meets the mechanical pressure of brushing. This transition is governed by rheology, the study of how complex matter flows under stress. Delivering that exact sensory experience every morning requires an industrial environment dedicated entirely to the precise control of fluid dynamics. Modern oral care megafactories operate with pharmaceutical precision, housing miles of mirrored steel pipes and towering silos where raw chemical elements begin their transformation. The process begins by feeding massive quantities of microscopic silica and liquid glycerin into mixing hoppers. These elements serve opposing roles. The dry silica particles are designed to scrub away plaque, while liquid glycerin traps moisture to prevent the paste from drying out into a gritty sand. As heavy planetary mixers churn this thick slurry, the sheer force of the blades inevitably pulls microscopic pockets of air into the mix. Trapped oxygen would cause the final product to oxidize and lose its potency, while the expansion of that gas would cause finished tubes to bloat and burst during shipping. To strip away every gas bubble, the mixers are sealed and the entire kneading process takes place under extreme negative pressure. This vacuum extraction forces the raw ingredients into an impossibly dense, smooth gel. The most delicate phase of production occurs when the red and blue-colored gels are injected into the white base. These different pigments must flow through the machinery under high pressure without bleeding or mixing together. Using laminar flow, coaxial nozzles pump streams in perfectly parallel lines. The colored gels and white base possess identically engineered viscosity, ensuring they move together. Under high pressure, they act as flowing liquids. When pressure hits zero, they structurally lock, instantly freezing the stripes. This structural freeze ensures the colors remain perfectly distinct and stable inside the tube until extruded. The final packaging line is a massive, high-speed pneumatic operation specifically designed to capture the gel without disturbing its internal geometry. Filling occurs from the bottom up. Injecting the paste into the open base of the tube directly eliminates air voids and preserves the striped alignment. Once filled, automated robotic jaws vibrating at ultrasonic frequencies clamp the plastic ends, using high friction to weld the tube shut. This structural freeze ensures the colors remain perfectly distinct and stable inside the tube until extruded. This hermetic seal locks in volatile mint oils, maintaining the specific texture of the engineered fluid. Throughout the run, optical scanners evaluate the color separation, while mechanical actuators squeeze sample tubes to measure the extrusion force. These automated checks ensure the paste responds correctly to the grip of a human hand before it leaves the facility. The scale of this operation allows a single production line to mix, fill, and seal over 800 tubes every minute. Automation handles the volume, but human rheologists perform the final quality checks. They smear samples between glass slides to inspect the microscopic distribution of the silica. They are looking for perfectly rounded grit. These particles must be aggressive enough to polish the teeth, but smooth enough to leave the enamel undamaged. The next stage of this science involves microencapsulation, where flavor compounds are locked inside microscopic polymer spheres suspended within the gel. These spheres are engineered to remain stable in the tube, only to rupture when they experience the specific physical friction of toothbrush bristles. The glossy ribbon on your brush is the result of a violent manufacturing process, tamed into a state of stable, functional geometry through chemical engineering.